Uh, Thank you very much. Thank you for the introduction. It's great to be here. There is amazing density of mathematics per square meter. I'm going to be talking about an old and well-known conjecture in graph theory. And my goal is to map out recent progress and current challenges towards this conjecture. And I'm very glad that there are so many young people here. Really, I mean, one of the reasons I got attracted to combinatorics and to graph theory to begin with is that the entry threshold is low. You don't need to know too much to actually make meaningful progress, and I believe that this is an important conjecture, and so I encourage you to think about it. All right, so the story starts at the same place as very many stories in graph theory, at the same place as Robert Tarjan life achievement talk started yesterday with Francis Guthrie more than 150 years ago. So Francis Guthrie was an applied mathematician, actually a cartographer, and he was solving a problem. He was actually trying to create a map of counties in England, so assign colors to counties, so that the counties sharing a border receive different colors, a distinguishing. And he noticed that he could do it using only 4 colors, and being brave, based on this one example, he conjectured that this is possible for every such map. So he famously asked this question, which became 4-color problem, whether every planar map consisting of contiguous regions, so every region needs to be not have islands, can be colored in 4 colors so that adjacent regions are distinguishable. And this question motivated the development of graph theory for about 120 years until it was famously solved by Appel and Haken in 1976, who showed that the answer is yes. But as graph theorists, I mean, we prefer to work on graphs, so let me start by restating this problem, not as a problem of coloring regions, but as problem of graph coloring. So we replace every region by a vertex of a graph, and we draw an edge of a graph between 2 regions that share a border. And we can do it in such a way that the drawings of edges are actually still on the plane and don't overlap. That's easy to see. And so the problem becomes a problem of graph coloring. So we want to assign colors to vertices of our graph in such a way that 2 vertices which are joined by an edge receive different colors. So if we can do it with k colors, we say that the graph is k colorable. And just like Francis Guthrie, we're interested in coloring efficiently using as few colors as possible. So we want to determine this fewest number of colors, which is called the chromatic number. And let me just play with this definition a tiny bit. So this was a chunk of a map I took from previous slide. It admits a four-coloring, so this graph is four-colorable, and then one can look at it a bit closer and actually see it's not completely efficient. One can three-color this particular graph, but one cannot color it with fewer than three colors because there is a triangle in this graph, three pairwise adjacent vertices, so they need three different colors. So that shows that in this example, chromatic number is 3. In general, determining chromatic number is a very hard problem, but the four-color theorem in this language, it says that every planar graph is four-color. So it's an incredibly famous theorem, but one of the reasons it's famous, it was the first major proof in mathematics that is computer generated. And in fact, to this day, even though there are better and better proofs which are computer verifiable and more easier to accept in various ways, there's no proof that can reasonably considered to be human verifiable or human readable. The shortest certificate which demonstrates that four-color theorem is true would be about 10,000 pages long. And in principle, it's readable, but why would you believe a person who read it, who says it's true, right? It doesn't provide any insight. Another point about four-color theorem is that it's a bit of a matter of pride of graph theorists that even though this theorem can be potentially formulated, sometimes naturally, sometimes less so, in terms of, in very different settings, in terms of different time equations, Lie algebras, temporally Lieb algebras, in various ways, the solution, computer-based, actually uses very, very classical, very much graph theoretical methods. All right, so where do we go from here? Well, I mean, we want to, people wanted to understand the reason why four-color theorem is true. I mean, so we now know it's true if you are willing to believe a computer, but why? And a key notion which leads to the formulation of the Hadwiger's conjecture, which actually is an attempt to understand it in four-color theorem, is a notion of minor. It's a notion of graph containment. So a graph H is a minor of a larger graph if we can obtain it by doing the following operation. One is two unnatural operations of getting a subgraph. You can delete vertices and edges. And there's one more operation which is called contraction. Again, it's fairly natural, where you take two vertices joined by an edge and collapse them together. So now they will be joined to all the neighbors of both. And in this setting, so one of the first theorems about minors and a classical theorem about graph structure is a characterization of planar graphs in terms of minimally non-planar substructures. So it says that a graph is planar if and only if it doesn't contain K5 or K3 as a minor. And so in this language, this theorem, which also was mentioned by Robert Tajan, it's says that four-color theorem can be reformulated that if you don't have K5 or K3 minor, then your graph is four-colorable. And it was already known to Wagner in 1930s that you don't need to exclude K3. So it's there is a structure theorem which says what happens if you only exclude K5. So Focal's theorem implies, in fact, is equivalent to the fact that if a graph has no K5 minor, then it is four-colorable. And one can also clearly not do better, say. You cannot say if you're, well, it's also clear for Focal's theorem, but in general, we know that, say, if you only have, so K5 here denotes a complete graph. Yeah, I'm using this notation. Let me explain it. In general, KT is a complete graph on T vertices. So it has T vertices and every two vertices are adjacent. So you might need four colors when you don't have K5 minor, if you, for example, if you're a complete graph on four vertices. So the bound on the number of colors is tight. And Hadwiger conjecture, again, kind of as bravely as the Francis Guthrie conjectured for color theorem for coloring based on one example, conjectures that one can generalize this statement by replacing the constant 4 by a variable. So Hadwiger conjectured that in general, if every graph which doesn't have a complete graph on T plus 1 vertices as a minor can be colored, properly colored with T colors. Okay, and that's the conjecture. In some way, just as before the solution of the four-color theorem, four-color problem was leading a lot of development in graph theory, a lot of development of techniques in structural graph theory and graph coloring. So large graph theory grew, but still in a large fraction of graph theory was motivated by this conjecture for a while. Okay, and let me tell you what's known about this conjecture. For T at most 2, it's easier. For T equals 3, it was already known to Hadwiger when he formulated this conjecture and was observed independently and earlier by others. For T equals 4, as I mentioned, it's equivalent to the four-color theorem. And for T equals 5, in a tour de force result, Robertson, Seymour, and Thomas proved in 1990s that it also holds. So it's a stronger result than the four-color theorem. And the proof was long, about 80 pages, and 80 difficult pages, and computer-free. But it used the four-color theorem as a black box. So, I mean, it's a stronger result. And it's wide open before that, after that. Okay. So I will discuss various open questions related to Hadwiger's conjecture. And I will present some challenges that remain to us. And thank you, by the way, for literally rising to the first challenge that you had today, which is attending this talk at 8:30 a.m. But some of the challenges that remain are even harder than that. And the zeroth challenge would be to actually have a reasonable proof of four-color theorem. I mean, lots of people try all the time. And fail. But I mean, you might succeed. I mean, I used to present exponential improvement on Ramsey numbers as an open, extreme open question of this magnitude, and it was done a couple of years ago, so who knows? Also, I mean, my advisor, PhD advisor used to mention during my PhD, you know, I mean, there are many major results in graph theory that you can solve and become famous among mathematicians. But if you want to become famous among non-mathematicians, so say to have your result discussed in New York Times, that's probably the only thing that he knows about that would do it. Okay, so this is a conjecture, so it is a generalization of already very different question. And I mean, at least from my point of view, I mean, the only way I can see this being solved within, say, next 20 years, I mean, I hope I'm too pessimistic, maybe I'm too pessimistic, is that it's false. I don't really know any reasonable pathways to positive solution. But in some ways, it also frees us up a lot. If the conjecture seems currently out of reach, we can play around with it. We can see what we can do by making it easier in various ways. And it really creates a whole, a large variety of problems which could be attacked with different methods. And they do provide us with some insights in problems in graph theory. So it's good to think, I mean, of this conjecture as somehow a guidance. So somewhere far this way truth lies. And well, maybe we cannot reach there, but we can go in that direction and get some smaller interesting truths along the way. And so I will discuss various, hopefully natural relaxations of this conjecture. So what can we do? So we are asked to show that every graph with no complete graph on t plus 1 vertices as a minor is t colorable. Well, maybe, I mean, let's not be too ambitious. Let's not color with t colors. Let's color with f of t colors, where f of t going to be bigger than t, but as small as possible. So that's one variation that we can try. Another variation, if we want to show that excluding complete graph on t plus 1 vertex makes us t colorable, well, maybe let's not, complete graph has a lot of edges, right? All the edges. Maybe let's be less ambitious, exclude some smaller graph on t plus 1 on t vertices, see what happens. So change what graph we're excluding. What else can we do? A notion of colorable is very precise. Every two vertices which are joined by an edge must receive different colors. We can try to make this less restrictive, and I'll introduce a precise notion. And here, I mean, the direction I want to look at, actually, I mean, one can describe it as coming from coarse geometry. We want to step away, far away from our graph and look at it from far away and see what happens. And still, there is something meaningful that we can prove. And the final variation which I will discuss is actually not a relaxation, which, I mean, in some ways is a bit icky. It's already a very strong conjecture. It's a strengthening, where instead of a minor, we will want to find something stronger than a minor. And I mean, that's new. I mean, if true, it could provide us, right? I mean, sometimes, and it's fairly common, Simon mathematics, proving something stronger could be an easier thing. Here I don't believe in this, but nonetheless, I'll introduce this. Okay, so these are 4 directions in which we can kind of play with the conjecture, and let me discuss what's been done. So here is the first direction. We want to prove that every graph with no complete graph on t plus 1 vertices or minor is colorable with some number of colors, depending on t. Well, let me first look at small t. So everything is known when t is at most 5. What happens with t6? So it's known that every graph with no k7 minor is 8 colorable. Every graph with no k8 minor is 10 colorable. These are currently best results. And so that offers the following challenges. This is still hard. It's not for color theorem, but try to do the next case of Hadwiger's conjecture. Shows that every graph with no k7 minor is 6 colorable. Here is a slightly easier challenge. It's not even known that every graph with no k7 minor is 7 colorable. Sounds like it might be a lot easier. Me and my collaborators, Denik Dvorak, and my student, Jeremy Turcot, spent half a year on this, and we were not shy about using computers. And we cannot do it. So it's still hard. Okay, but that's small t. I want to also think about what happens for large t. And here is one kind of guiding example to what we can expect. So we know that every graph is no, we know because of for color theorem that we need to allow, probably if we don't have a computer-free proof of it, an extra 1 or 2 additive constant in terms of number of colors. But do we need more? There is a very important special case. Suppose we have a graph where there is no triple of vertices with no edges between them. Then every color class, you cannot color any 3 vertices with the same color. So you need at least n over 2 colors. So every graph with no independent size of set of size 3 should have k n over 2 minor. But the best that's known is that every such graph has k n over 3 minor. Nothing better than 1/3 is known. So there is a multiplicative gap between what's known and what is believed to be true in this case. And in fact, Paul Seymour, who is probably the expert currently on Hadwiger's conjecture, he believes that if the conjecture is false, it's false here. So solving this case is the most important. But in the positive direction, improving the constant 1/3 to anything 0.33334 would be a major thing at this point. But it also tells us that, okay, so that's a special issue, but suppose we want to sidestep not only this, but not only the 4-color theorem, but this. So suppose we don't want to solve this. This is hard. Then the best we can do, in some sense, is to prove a linear bound on the number of colors. So proving that there exists some constant C, absolute constant, so every graph with no kt minor is colorable with C times T colors. That's open, and it would be very major, but we've been getting closer. And so to explain how we were getting closer, let me very quickly, and set up the rest of the talk, let me very quickly explain how easy cases of Hadwiger are easy. Remember I said that for T at most 2 it's easy, and for T3 it's also well known. Like, for example, so what does it say for T equals 2? Every graph with no K3 minor is 2 colorable. So what is a graph with no K3 minor? It has no cycles. So it's a tree. So why is every tree 2 colorable? For many reasons, of course it is. But here is a kind of general helpful reason. I'll say that a graph is D-degenerate if I can order its vertices from left to right, so that every vertex sends at most d edges to the left. Then it's easy to see that every d-degenerate graph is d plus 1 colorable. Color from left to right greedily. There will always be a color. Right? So if you only send one edge to the left, then you can always color. And that's one reason why trees are too colorable. Right? You can always arrange vertices from the root by their distance, and then everybody has unique neighbor to the left. And for all easy cases of Hadwiger, it's true that just this degeneracy works. So every graph with no K3 minor is 1 degenerate, every graph with no K4 minor is 2 degenerate. It breaks at the 4-color theorem. But basically this very simple thing is kind of the most robust thing we know for coloring. And for a long while, this should be Thomasson. That's a bad misprint because that's a different person. Kostechka and Thomasson in 1980s proved that every graph with no KT minor is a T root log T degenerate, and so T root log T colorable. And that was the best bound for about 40 years. And the problem is that this bound is tight. Degeneracy method goes no further. So if all we have is degeneracy, then this might be the answer. And in fact, I mean, the bound stayed at this level, and our lack of methods was a bit of an issue that Reed and Seymour mentioned in the late 90s, that there is a popular Hadwiger counter conjecture that this is right. That T root log T is actually the right bound. But fortunately, it's not. So a few years ago, first with Zisha Song and then Luke Postel joined us, we improved the degeneracy bound, reducing the power of the logarithm from 1/2 to 1/4. And that led to a flurry of further developments by Luke Postel, mostly with courses. And now the bound sits at a comfortable T log log T. So the ratio between what's known and what's true was significantly reduced to make it logarithmic. And now, so Luke Postel has his own Hadwiger's counter conjecture. He believes that the best that he can do is the truth. I think, well, I don't know. Okay, so that's the state of view on the number of colors you are required. Now, let me say a few things about what can one do if one doesn't want a complete graph on T vertices as a minor, but some less dense graph. And let me start at the same place I started the discussion of the previous variation. At the smallest value of T for which Hadwiger is not known. So we are excluding a graph on 7 vertices, and we try to 6-color the graph. By the way, you cannot, I mean, if you exclude any graph on 7 vertices as a minor, you cannot hope to use fewer than 6 colors, because just complete graph on 6 vertices needs 6 colors. So kind of the setup, we are going to be excluding graph on 7 vertices and trying to 6 colors the resulting graph. And an old theorem of Jacobson from 1970s said that you don't need to sparsify complete graph on 7 vertices much. You can delete, so you always will, if you cannot seek scalar, you will always have a minor which is almost complete graph on 7 vertices. It only misses 2 edges. Okay? And where do we go from here? Well, we want to go to case 7. We wanted to go to deleting 1 edge, but even that turns out to be ambitious. Okay, then what can we do? Well, there are 2 ways of deleting 2 edges. You can delete 2 edges which share no ends, or you can delete 2 edges which share an end. And Jacobson's theorem says that sometimes you get one of them, sometimes you get the other of this minus. And for technical reasons, it's really, really important to exclude both. And very recently with my master student, Agnes Tochnik, we bravely extended this result, showing that it's okay, if we are not six-colorable, we always get one of these 2 graphs. We don't need to exclude both. And that's already some work, but not too much. So that's a reasonable thing. There's still an open question here. Is it true that the other graph with deleted 2 edge matching always is a minor? We cannot do it. Okay, but again, now let me move from the setting of when t is small to more asymptotic setting where I'm thinking of t as large. And there is this meta-conjecture of Seymour. I don't know if I should call it a conjecture. It's for each graph H, it represents a conjecture. When a graph is complete, it's Hadwiger's conjecture. But for other graphs, it can be, well, so this whole palette of conjectures are referred to as Seymour's H-Hadwiger conjecture. So for any graph on t plus 1 vertices, excluding this graph as a minor should make it C-colorable, and that should be optimum. So for which graphs H can be proved? And there were some results already. So for complete bipartite graphs where one side has size 2, it was proved by Rudall. When one side is significantly larger than the other side, it was proved by Kostechka. And with my PhD student, Jeremy Turcotte, we proved something that this conjecture holds for a large, less structured, right? These are very structured, like you know exactly what type of graph it is, class of graphs. But the definition is a little bit awkward, so let me explain it. We prove that this conjecture holds if the graph that you are excluding is large, has bounded maximum degree, is bipartite, and is planar. Lots of conditions. But let me explain why this is a meaningful theorem. So what we really proved is that for these graphs H, the degeneracy method works. So for this graph H, if they have t plus 1 vertices, every graph with no H minor is t minus 1 degenerate. So just degeneracy works. And that's no longer true if I forget any of these words I inserted. So if I allow it to be planar bounded maximum degree, forget bipartite, it's false. If I forget bounded maximum degree, it's false. If I still have bound maximum degree and leave it bipartite, forget planar, it's also false. Planar is just for your sake. Really, the real condition for those who kind of know about it is not planarities. structural sparsity, you need not to be an expander. You need to have strongly sublinear separators, the graph. So basically, it's not that planarity we need, it could be from any fixed minor closed class or even looser, but you really need not be an expander. It's false for expander graphs, for cubic expander graphs. So that's a different direction. And so I'm saying that none of these conjectures conditions are omitted, but I'm a bit lying. So as I said, planar can be replaced by something. Bipartite cannot be omitted, but could be replaced potentially by, say, 5 colorable. I don't know. Bounded chromatic number could be enough. And so a challenge here is to continue, in this direction. So prove this Hadwiger's conjecture for other large classes of graphs. And potentially, can you get even closer to the characterization of graphs H? For graphs H, for which degeneracy works. So that's a second direction where we think of our graph as that we exclude, not complete, but specify it. It seems like you need to specify a fair bit. Okay. So let me talk about a third direction. So here we will try, we will relax the coloring. We will not color properly. So let me try to explain what I mean. And really, the idea is that we imagine our graph that we are trying to color as being extremely large. And we look at it from the point of view of coarse geometry, where we walk away from our graph towards far, far away, and which only makes sense for infinite graphs, but bear with me. And we look at the coloring from far away, and we want that color from far away if we are nearsighted. We want it to look proper. So what does it mean? It means that the blobs of color don't propagate too much, right? They bounded size. So we just want a components of every color class to be of bounded size. And that's what we take as a definition. So I'll say that a class of graphs is coarsely T-colorable if there exists some bound absolute for all class, so that every graph in this class can be colored using T colors, so it's no longer proper, so we allow adjacent vertices to have the same color, so that every connected monochromatic subgraph, so that any connected component is a bounded size. That's far away thing. And the coarse Hadwiger conjecture was proved recently by Dzymovich, Perret, Norin, and Wood. They proved that a class of graph with no kt plus 1 minor is coarsely T-colorable. Zdeněk Dvořák and I announced this result a few years ago before that, but our preprint is not available. And now finally there is a proof. This is hard. This is again an 80-page clever paper, and it uses graph minor structure theory. There is this beautiful theory which tells you how large graphs with no particular minor look like. But so let me tell you a little bit the directions in which this can be improved. One theme that, I kind of like here is that some degeneracy is, our main point of reference. Is it true that every graph with no kt plus 1 minor is coarsely T-degenerate? What does it mean? What is a degeneracy from a coarse point of view? So one can think of it this way, you, again, step back, so you have these chunks of size, you order your vertices divided into chunks of size C, so that every chunk sends only a few edges to the left. But that's a bit strong. There is a weaker notion. So a graph is coarsely T-degenerate if you can order it into chunks, and divide into chunks, order them, so that every vertex has at most T-1 neighbors in the previous sets. And it's easy to see that it implies coarsely T-colorable. So in the unpublished theorem of Stein-Dvorak and I, we replace this T-colorable by T-degenerate. So we can believe we can prove the degeneracy version. But here's another side note. Hadwiger's conjecture is super nice because it's exact. If you exclude KT plus 1 minor, you are coarsely T-colorable, and you need to exclude KT plus 1 because KT plus 1 is not T-colorable. You cannot exclude something else. You better exclude complete graph on T plus 1 base. Here it's not clear. Why do you need to exclude KT plus 1? I mean, KT plus 1 itself, complete graph on T plus 1 vertices, is coarsely one colorable. Just color it from far away, it looks perfectly fine. So there are conjectures at what is truth here, and they are open, so there is still a challenge, and we are getting closer to solving this challenge. Describe exactly minor closed classes of graphs which are coarsely T-colorable or coarsely degenerate. It's surprising thing here is that these asymptotic, very kind of large-scale questions could be easier to solve. I mean, this is way more enriched, exactly understanding answer to this question than exactly understanding answer to Hadwiger's conjecture. Okay, and now finally, let me talk about another notion which goes in a different direction. It makes things harder rather than making things easier. So we are going to replace a notion of minor by a more restrictive notion. So before stating this notion, let me reformulate the notion of minor. Instead of talking of complete graph on T vertices as a minor, we can talk about a model of a complete graph in the graph. So what is a KT model? It's a collection of pairwise disjoint connected subgraphs, so that if you contract them, you get a complete graph on T vertices. So for each subgraph, for each pair of subgraphs, there is an adjacency between them. Right? So a model is more or less a recipe how to get a minor. Right? You contract these things to vertices. And you have a model exactly when you have a minor. So it's equivalent characterization of having a minor, having a model. Okay, now let me play with this a little bit. Suppose I don't want these subgraphs to be connected. So suppose I want a KT model where I just have a subgraphs and an edge between every two subgraphs. Then if I cannot be colored in T-1 color, I can get such a model very easily. I try to color greedily. If I need to use color J, means I cannot use color I. That means my new vertex is adjacent to a vertex of color I. Okay, this is a bit, maybe a bit big, but if you think about Hadwiger's conjecture in this direction, it feels like the following stronger thing might be true. So here is a stronger notion of model. We will search for pairwise disjoint non-now connected subgraphs. so everything is the same, such that for every pair of these subgraphs, every vertex in the later subgraph has a neighbor in the previous subgraph. That's way stronger than just one vertex. And the point here is that it's somewhat natural. If you forget connected, it's still true that if you are not T minus 1 colorable, you have a dominating KT model. So a question arises, is the corresponding strengthening of Hadwiger true? Is it true that every graph with no dominating KT model is T minus 1 colorable? So that seems way stronger. And here is a challenge. I mean, please prove that this is false. I mean, I want Hadwiger to really be kind of the border of what is true. I mean, if something like this is true, it's a bit distracting, right? I mean, what are the reasons that this is true? But we cannot disprove it so far. It might be true at the moment. Everything. So we spent a month last year with Antonio Girao, Yurita Mitsugama, and Jane Tan trying to do this. And all we got were positive results. We can almost prove dominating for color theorem. We are very close. One thing that we can prove that if there is no dominating KT model, then we are T log squared T degenerate. So this might be false, but it's not terribly false. Right? So we are still within logarithmic, polylogarithmic factor. So that's another direction. And this last challenge, I mean, I hope this is the most doable. I mean, let's put the most ambitious result possible back where it used to be at Hadwiger's conjecture. I mean, there were many strengthening of Hadwiger's conjecture over the years. There was famously Hodges' conjecture, where instead of a minor, you forbid a subject. And most of them are false. It's great. So, I mean, Hadwiger's conjecture, not only it remains open, most of the strengthenings that were proposed were proven to be false. So this one that remains. Okay, and let me just very quickly summarize. So this is a conjecture. I mean, it has been pretty important for a while. It's currently seems to be out of reach. But in various, I mean, we're kind of trying to circle it. We're trying to approach it from all different directions, and we're getting a little bit progress, and we are learning. I mean, I feel like we are learning more about graph structure, more about graph coloring by pursuing this. So again, let me reiterate, I feel like this is, I mean, kind of a good compass, good pointer of the direction in which one can go to do research in this area. Thank you.
Sergey, thanks a lot for your nice talk. Any questions or comments?
Hi, and thank you for a nice talk. So I want to ask, can you say a bit more about the proof of the result on the K7 minus 2 edges result, or your result about getting one particular K7 minus 2 edge where these two edges share an end?
Yeah, sure. So, I mean, the difficulties are mostly still around this question of degeneracy. So you want small degree vertices, and then there are techniques, some standard techniques of what to do with the small degree vertices. So one goal is to show that every graph with this particular minor has many vertices of degree. Turns out 7 is the right bound, of degree 7. Now it's believed that every graph with no K7 minor even must have vertices of degree 7. But, and that sounds innocent, but it's hard to prove. So to do this, we prove just the number of edges that the number of edges that the degrees on average of such a graph must be below 8, right? Average degrees below 8. But that's not true. You need it to be highly connected. And basically, I mean, that's where, 10 out of our 17 pages go into. It's hard to prove results for highly connected graphs by induction. You need to preserve connectivity. I mean, it's a technical issue, but to solve it, we need to kind of sharpen current tools.
The solution of this, how large is the constant C?
Oh, I'm not sure it's even computable. Because we are using, I mean, at least the way we are doing it, I mean, maybe the other group is gentler. We are hitting it with the hardest core graph minus theorem, including well quasi-ordering. So
But the C is the absolute constant, or C is a function of T?
it's function of T. Yeah, of course. Yeah, and some terrible, terrible function.
In the previous result, the error graph that is not six colorable has a subgraph of K7 minus, but K7
Minus 2
minus,
edges. Yeah,
but K7 minus itself is
open.
six colorable. Why? So is there any? So why this subject? Why this structure is so different?
I mean, it's just so. I mean, it's technical. I mean, it's unclear why. I mean, they're just trying to push what we can do as far as possible. Right? So it would be good to prove that K7 minus 1 edge, if you exclude that as a minor, the graph is 6 colorable. But there are a lot of, I mean, we tried, we couldn't do it.
Thank you.
Any more questions? Sergey, you told us about the conjecture and the counter-conjecture, and at some point in the middle of the talk, you tried, it seems, to tell your personal opinion on, like, is it true or where we stand with the counter-conjecture? Maybe you can expand a little bit.
I mean, I don't know. I mean, I'd like to. So Jim Gillen, who is kind of one of the experts in structural graphs, he is of opinion that you always just need to believe the most beautiful thing. That's the right thing to do. I'm not sure about this. Personally, I think I don't care that much. So what I believe is that if the conjecture is false, it's for a silly reason. That somehow, that at least weak Hadwiger's conjecture should be true. And if conjecture is false, it's somehow, there is some strange graph with no K20 minor, which cannot be 20 colored. Well, I mean, that's okay. Doesn't really change things globally. I mean, that's what my opinion.
And at the very beginning, you told that you can state at least the four colors theorem in terms of, say, temporally Lie or some Lie theory. Does it like help in any way?
Well, it doesn't seem to, right? I mean, that's the thing. Yeah. None of this is used. I mean, there is a very pretty formulation in terms of bracketings of cross products of basis graphs in 3 dimensions, but I mean, I can't quite explain. Basically, I mean, there is a formulation of four-color theorem which really doesn't use any fancy math, sounds innocent, and like must be true, but doesn't really. I mean, none of these formulations actually helped with eventual solution.
Okay. Any more questions, comments? Then let us thank Sergey again.